Alright, so what we want to look at now is we want to look at rotations and rotation rates and what we used to call speed before, and now we're going to relabel it and call it linear or tangential speed. So to start exploring rotations, let's take a look at, let's say we have a circular track, and the center of the track is the center of the circle. And what we're going to do is we're going to line up a bunch of little runners in a line. And all of our little runners are in a little line. And what they're going to do is they're going to run as a solid line around the track. And so when the runners are running around the track, what we used to call speed before, when the runners are running, that was what we used to call speed. But when we run speed on a circle or a curved object on circle, speed on a circle is now going to be called linear or tangential speed. So whenever we have what we used to think of just before as speed, like somebody's movement rate, if you take that movement rate and you do it around a circle or some type of oval or whatever, the idea is once you do that, you move from what we used to call just speed. We now need to call that linear or tangential speed. So the idea then is our runners are all running around the track in a solid line, and what we want to think about now is all these runners are running around the track, if they're running as a solid line around the track, they can't have the same linear speed, can they? No, of course they can't. Because this guy here is doing what? He's running this big dashed circle. The guy in here is running a small dashed circle. And so we know that the linear distance this guy is covering, because we know the circumference of the circle is 2 pi r. So the idea is, let me try to improve that's the inside guy, and that's the outside guy. And so you can see the inside guy runs his circle, his circumference is much smaller. So if those two guys are running the circles, the guy on the outside must have a higher linear speed or tangential speed because he has to cover a greater distance in order to keep up with the guy on the inside. So there's some type of relation between your speed and how far you are away from the center of your object. Now what we want to do, so we have this idea. Let's keep this in the back of our mind, this idea of linear and tangential speeds, and where you're on the circle being different. Now let's pretend that instead of us having a line of runners, we are on a merry-go-round. And what we're going to do is we're going to take a solid line on the merry-go-round. And this solid line now rotates because the whole merry-go-round rotates. Now, what we're going to do is we have our linear speed. Now we need to think about our rotational speed. Rotational speed or rate of rotation. Now, when we think about rotational speed, the easiest way to think about it would be just to stand over here and count the number of times this black line goes by you in a given amount of time. And that's exactly what a rotation speed is. So rotation speed is either the number, it's like the number of rotations or revolutions per unit time. And this is the definition of a rotation speed. So, you know, if the thing went around 3 times in a minute, its rotation is 3 rotations per minute. Or you could break that down into rotations per second. Now, one other thing that we do is we can count the number of revolutions. Like, you know, the object rotated, it had 3 revolutions. And if you don't want to use the word rotation, you can use the word revolutions and say, oh, it's revolving 3 times per second. Now, in physics, one way we measure rotation speed is we know that a circle is 360 degrees. If you go around an entire circle, you've covered 360 degrees. Well, the unit we use for that is 2 pi. So there's 2 pi, what we call radians, in 360 degrees. So when you walk around the entire circle, you've covered 2 pi radians. And so what you do is you measure your rotation speed in radians per second. So you'd be like, oh, I covered 2 pi radians per second. So that means you did 1 revolution per second, since there's 2 pi radians in 1 revolution. So if you knew that you, let's say you completed 2 revolutions in a second, you could take your 2 revolutions, multiply by 2 pi. That would mean you did 4 pi radians in a second, because every 1 revolution is 2 pi radians. So this is the rotation speed, is usually in radians per second, and we call that omega. So omega is your rotation speed, and it's just how many times your object rotates in a certain amount of time. And in physics, usually we use the units of radians per second. So now let's try to take a look and get a relation between our rotation speed and our linear speed, because this whole line is rotating at a constant rotation rate. But in order for that whole line to rotate at a constant rotation rate, that means the thing out here at this dashed red line and this thing at this inner dashed line have to be at different linear speeds. That's what we came up with. So in order for these 2 linear speeds to be different but have the same rotation speed, what has to be true? Well, this is what we find out. That there must be some relation between v, our tangential speed, the radius, and omega. Because we said out here, or we'll just do it, we'll write this out, that there should be a relation between the tangent speed has to be something with the radius and the rotation rate. Because this out here and this in here are rotating at the same speed, but they have different linear speeds. And the only difference between these 2 points is how far they are away, their radius. So when we have this equation, it's v is equal to r times omega. So their rotation rates are the same. The only difference is how far away they are from the center of rotation, and that tells you what their tangent speeds are. So when we're thinking of objects rotating, we now know that we redefined our speed to be linear or tangent. We have this thing called rotation rate, which is our omega, and it essentially is how fast we're going around our circle in a unit time, per unit time. And we have a relation between our tangent speed and our rotation rate. V equals r omega.